All right, let's tackle one of those programming problems that everyone labels hard, finding arithmetic subsequences. But what if I told you the solution isn't some crazy, complex code, but really just a single, beautifully simple idea? Trust me, by the end of this, that elegant idea is going to feel totally intuitive.
So, take a look at this array. Seems pretty straightforward, right? But believe it or not, there are 7 distinct arithmetic patterns hiding in there. Go on, you can even pause and see if you can find them all. Yeah, it's a little trickier than it looks. And that's the puzzle we're going to unpack together today.
Okay, so before we can start counting anything, we have to make sure we're playing by the same rules. What exactly is an arithmetic subsequence? Let's break down the 2 key puzzle pieces.
First up, an arithmetic sequence. And here's the absolute most important rule. It has to have at least 3 elements. Why? Well, with just 2 numbers, you can't really say you have a pattern, right? So 2, 4 is just a pair. But 2, 4, 6, now that's a sequence. And this one little rule, it changes the entire game.
And second, we have the subsequence part. Now this is where things get really interesting. The numbers don't have to be right next to each other in the original array. We can literally just pluck them out from anywhere we want as long as we keep them in their original order. And all of a sudden, the number of combinations we have to check just goes through the roof.
So that's our mission. Find every single one of these arithmetic subsequences that has 3 or more elements. Now you might think, I'll just check every possible combination. But trust me, that's an exponential nightmare. It would take practically forever. This problem isn't about muscle. It's about finding a much, much cleverer way in.
So where do we even begin with a problem like this? Well, we start small. Instead of trying to find these big, long sequences all at once, let's think about how they're even built. I mean, every sequence of 3 or more is really just a shorter one with an extra piece tacked on at the end.
Remember that 3-element rule we just talked about? Well, think about it. Any valid sequence, like 2, 4, 6, is just a simple pair, 2, 4, with one more number added on. That is our entry point. Instead of looking for finished triplets, we're going to start by just looking at the pairs.
And this brings us to the single most important question in this entire explainer. If we just pick any 2 numbers from our array, let's call them nums I and nums j, the real question we need to ask is this: how many existing arithmetic sequences could this new pair perfectly extend?
And answering that question, that leads us to our big aha moment. The technique we're going to use is called dynamic programming. Now, don't let the fancy name scare you. All it really means is that we're going to solve this huge problem by solving tiny little versions of it first. And then, here's the smart part, we reuse those results to build up our final answer. No wasted work, just build.
This is it. This is the entire secret sauce. To figure out what our new pair nums of j, nums of I can do for us, we just have to look at its first number, nums of j, and ask it a really simple question. Hey, how many sequences with this exact same difference were already ending with you? That's it.
Now, to pull this off, we need a place to store our answers as we find them, kind of like a memory bank. We'll call it F. So FID is just going to store a very specific number for us. It's the count of arithmetic subsequences, length 2 or more, that end at index I and have a difference of d.
Okay, theory's done. We have our main idea and we have our memory bank. Now let's actually put it into practice. We're going to walk through the logic step by step and see how we fill up that memory bank and get our final answer.
So here's the flow. We start by picking an endpoint nums I, and we loop through the whole array. Then, for each I, we look backwards at every element before it, nums j. Next, we calculate their difference, d. And here comes the magic. We look up in our memory bank how many sequences ending at j already had this exact difference. We add that number to our final answer. And finally, this is crucial, we update the memory bank for I, getting it ready for the next steps.
Okay, let's trace this with a simple 2, 4, 6. Let's just focus on that very last row. Our endpoint I is at index 2, which is the number 6. We look back to j at index 1, the number 4. Their difference, d, is 2. So now we ask our memory, how many sequences ending at index 1 had a difference of 2? The table tells us the count, CNT, is 1. That's from the 2, 4 pair we already found. So we add that 1 to our total answer. And bam, we just officially counted the 2, 4, 6 sequence. Then we update the memory for index 2.
You know, if you look at the actual code for this solution, this whole complex idea really boils down to just 2 critical lines inside the loops. And if you can understand these 2 lines, you understand the entire algorithm. So the first key line is ants plus equals CNT. This is the payoff. This is the moment we find a valid sequence of length 3 or more, and we add it to our treasure chest.
So why does this work so simply? Well, you can think of it this way. CNT is basically the number of chains that were already built and just waiting at element j. Our new number, I, is the perfect next link for all of them. So by adding nums of I, we instantly extend all CNT of those chains, creating CNT brand new valid sequences. So we just add that number right to our total.
Now, the second key line is FID plus equals CNT plus 1. This one isn't about our final answer. This is about paying it forward. We're updating our memory bank so that any future loops that look back at our current number, nums I, will have the right information to work with.
So let's break down that CNT plus 1. The CNT part represents all those longer chains we just extended. We're basically telling our memory bank, hey, all those sequences that used to end at j, they're now one longer and they end at I. And the plus 1? That's for the brand new kid on the block, the pair nums of j, nums of I itself. It's a new chain of length 2, and we have to record it so that it can be extended by some other number later on. So, after our algorithm chugs through that whole process for our original puzzle, 2, 4, 6, 8, 10, what's the final count in that treasure chest? The process works perfectly and lands on the final answer, 7. And here they are, all 7 of them. You've got the simple ones like 2, 4, 6. You've got the longer ones like 2, 4, 6, 8. And then you have this beautiful one, 2, 6, 10, which perfectly shows off the power of a subsequence. It skips numbers in between, but still keeps that perfect arithmetic difference of 4.
So there you have it. We took a problem that's officially labeled hard, and we broke it down with one simple but really powerful idea. So what's the big takeaway from all of this?
I think the core idea is this. We weren't just counting things that were finished. At every single step, we were tracking the potential for future sequences to be built. We weren't just storing answers, we were storing possibilities.
And that really leaves us with a final question for you. This whole counting by extending pattern, this idea of solving a big problem by building on the answers to smaller ones, it's one of the most powerful tools you can have. So the real challenge is, now that you can recognize this pattern,